it out now. It's good. What's up, you scholars of enlightenment? Yesterday, JWST released its first full color images and spectroscopic data. And I think it's fair to say that all scientists around the world were pretty excited about them. I know my guests today are pretty excited about them, just as I am. The release represents the first wave of full color scientific images and spectra the observatory has gathered, and the official beginning of Webb's general science operations. But before that happens, I've had the chance to assemble a crack team of astronomers and space enthusiasts and artists who are ready to break down the science and art behind them and look at these fascinating images with me and tell me why they're so important, impactful, and far-reaching. So with us today, first of all, we have Jasmine Singh. Jasmine, how are you doing?
I'm good.
So Jasmine studies planetary and atmospheric science at Purdue University with an eye on being part of the search for life beyond the Earth. She has a fascination with all things space and has a very brilliant Twitter page, AstroJazz. I will put all the links down in the description, so head over there and take a look, where she shares all the latest space news and science. So be sure to check that out. We also have Julien Girard. Julien, how are you doing?
Sorry, I'm muting. I'm pretty good. I'm very good, actually. I put my full color shirt, for the full color images.
Very, very swanky. I like it. Right. This is the French are always more fashionable, Julien. This is the thing we know from the UK, right? Dr. Girard is a physicist and astronomer at the Space Telescope Science Institute in Baltimore, where he works as part of the JWST NEARCam team. And his research focuses on constraining our understanding of the demographics, formation, and migration mechanisms of long-period giant extrasolar planets and brown dwarfs. So, I couldn't ask for a better team to help me go through these images. We may be joined also by space artist Cathrin Machin, but she's a little bit busy at the moment. So we're hoping she'll get a chance to join a little bit later on. So, first thing I think, because this is going to be a pretty casual run through of these images. I'll come to you first, Jasmine. Your reaction to these images. Nice and casual. Just what are your thoughts of these images?
Yeah, definitely I had very high expectations for these images. But definitely when I was watching the stream, as they were revealing them one by one, I think my expectations were blown out of the water. I really, really love the images. They're super beautiful. I think the public, also agrees. We do have a few people that aren't as excited, but that's okay. I think we'll catch them later on, but I was really, really excited, really emotional. I think this is a huge time for space science, and yeah, we're gonna get some amazing results. That's really gonna advance astronomy, I think.
Julien, your thoughts as somebody who's been working very, very close to this. Was it relief, or was it excitement, or a mix of both? What was how did you feel?
Everything together. I cannot describe. For months I've been working on real images of Webb, like as part of the commissioning team. I had access to all the archive, and I was specifically working on some NIRCam images and some coronagraphic NIRCam images. So, you could think that I would not be that surprised. Of course, I knew, the image quality. I saw it every day. I saw it improved across the commissioning period. But seriously, I hadn't imagined, that they would be so deep, so crispy, and so mind-blowingly beautiful, especially, like 2 days ago, I was still like fighting with some artifacts in my images, like if you look at the raw images, they're nothing like that, so there's a huge work. And it's not just I'm not talking about the last Photoshop little bit, to make them very PR ready. I'm talking about some pre-processing of the raw data. I mean, infrared detectors are nothing like, the beautiful detectors we have in our cameras. It's pretty ugly if you look at the raw files.
So this is the stuff that nobody sees behind the scenes, right? All the number crunching, and they're
I
trying to
mean,
make the
actually,
detectors work correctly and all this kind of stuff.
I mean, it's all public now, so people can go to the archive and download the products, and they can see different stages. But yeah, generally that's the stuff nobody sees.
The thing that I found really interesting, Julien, and you tell me if I'm wrong on this, but the images seemed like a really good kind of tech demo, if you will, to show that all of the different aspects of this observatory are online. So we saw transits, we saw spectra taken of galaxies deep into the infrared. We saw beautiful images in the infrared in two different wavelengths. Was this the idea that you guys were going for? Was to kind of show that it's open for business now? We're ready to go on all of these different fronts.
Yeah, so I forgot to say that I hadn't seen those images because they were kept secret even from us. So there was, here at the Institute, they made some kind of special early release observation Tiger team, a team composed of about 2 people from each team. So there were 2 people from my team, 2 people from the NIRSPEC, NIRIS, MIRI team, etc. And a few project scientists from the, project scientists have their job definition is to make the observatory successful and scientifically useful, and do as much as possible so that the community can use it immediately, right? And so they are the ones that assembled this selection. I think they went from a selection of 80 or 90 interesting potential targets.
Oh, wow.
And then they went down to less targets and chose, as you said, an exoplanet spectrum with a fast period transit, and then a deep field, and then a star forming region, and then beautiful galaxies. Like this is, and it's funny because I was on shift when those observations started. And I could see where the telescope was pointing. So I couldn't see exactly where the telescope was
some
pointing.
Ideas
but
maybe of what it could be.
I found, for example, that it was observing the Stephan's Quintet, and I looked it up. I did my own research, and I saw the Hubble image of it, and I was like, oh wow, that's a good choice.
Yeah.
Especially the Spitzer image was not as great as the Hubble one in the infrared. So I was like, oh, that's the perfect one to go sharper on.
Yeah. We're going to take it, and we're going to take a look at those images. I've got the nice combination of Spitzer. Jasmine, bring you back in. What are you most excited about? Because you're a planetary scientist, right? So which images and what aspect of what Webb was doing in this kind of tech demo were you most interested in seeing?
Well, I think I was really interested in the exoplanet spectra that we got of WASP 96b.
Yeah.
Everybody talks about the images themselves. I think the public themselves really likes the beautiful galaxies and stars and nebulae. But us scientists are definitely more nerding out for the spectra and what that can tell us about different planets, far beyond the solar system. So I think I was more so excited about that, but I definitely really, really enjoyed the other images, especially, putting them side by side with Hubble, which I'm going to assume that we're going to be doing that, later in the stream. So I really think that's exciting, just learning about all these worlds that are super far from our own and what that can tell us about them. And maybe, which makes me really, really excited is if they are potentially habitable.
Definitely. And Julien, Jasmine brings up a really interesting point, that balance there between showing what Webb could produce in terms of beauty and in terms of basically art in effect, and the data that it actually produces, which, as we'll see in a minute, is super clean and, the most important thing, super quick compared to older telescopes like Hubble. So I think Jane Rigby said on the NASA live stream that they can produce, beautiful deep fields in sort of 10 hours, whereas this took Hubble sort of, a couple of weeks. So the speed at which you guys are able to produce data seems to be absolutely ridiculous. Julien, you might have seen this presentation this morning, or was it this morning or the other morning?
Yeah, so I was live
You were live
during
on this
the event. Yeah,
and
is that the one you're showing?
Let me zoom in a little bit because it might be a little bit difficult for you guys to.
Yeah,
to see as
so
well.
in fact, I missed some of Jane Rigby's presentation on the NASA Live because I was looking at this one, and this one I was going to talk about it. I'm one of the persons that asked to make it public because if some people want a little bit more science oriented, insightful explanations on the images and the spectra that were taken, that's a really good presentation. There, it's about 2 hours, and there's a menu. And for example, like the Stephan's Quintet, 5 galaxies. They also took spectra of some of the galaxies, and one turns out to have an AGN in the center, and that's all explained by David Law at about 1:05, 1 hour and 5 minutes in this feed.
I'll make sure I put that link down in the description so people can check that out. I think a beautiful thing that we sort of mentioned just before we come on to seeing the images is, and you'll know this, Jasmine and Julien, from just being people who work in the field. These images are all of things that we've seen before, so you can also see the beautiful improvements that you get with Webb relative to the older telescopes. And Julien, we did this quite a while ago before Webb was even fully up and running, comparing to Spitzer and comparing to ground-based telescopes. But I think it's a really nice choice, Jasmine, to have stuff that everyone kind of knows about in the field, and some people even might know about from looking at old images of this in the public domain, and to be able to see those improvements, right? We talked about off stream this lovely piece of work by is it John Christensen, where you can see the kind of side by side of these images. What do you make of them kind of imaging things that we already know about?
I think it was a really good choice because I was kind of live tweeting, during the event, like refreshing the page as much as I could, as they were revealing the images, because what I was doing was I was putting the Hubble images side by side with the James Webb images, like you're kind of, showing right now with the sliding thing. I love that site. But I was doing that and people were really amazed by it because you can really see the progression in the telescopes. And obviously Hubble has given us so many incredible images, such as Pillars of Creation, Mystic Mountain, stuff like that. And it was such a pioneer for its time, but now we have Webb, which is just really taking what Hubble did and just expanding upon it and showing us things that we've never seen before in those images. It's really just night and day. That's what I was seeing in those images.
Julien, have you seen this this side by side comparison?
Yeah. I actually reposted it. That's one of the first one that was made.
I was going to make some like dissolving ones, I was saying, and Jasmine's been doing some lovely comparisons, putting them side by side on her Twitter. But then when I saw this, I was like, yeah, okay, this is the real deal. What John has done in this.
Yeah, though I must say, I really like that. I mean, but I also really like to download the high resolution of the image and just go around with your just travel inside the image of the high resolution one. That's just mind blowing. Like the other day when the president of the United States revealed the first image. So first of all, everybody was a little bit grumpy because they were waiting for like 40 minutes with a not so great music, I would say.
Yes.
And then the president kept us waiting for quite a while. I saw somebody somebody had taken the holding screen and they'd put, it was like, JWST image momentarily, and they changed it to heat death of the universe momentarily, because it was like taking so long, and the music
No,
was
so we were going
interesting.
crazy on different chats that I was in with other astronomers, and the thing also is like when they revealed the image, you could just see like, you know, you couldn't see what it was really. You could see it was a deep field, but it was like back in their room, and then they cut the transmission. So, you know, I understand the people that are slightly, you know, disappointed at first because it's like, okay, another deep field, you know, and then, but then you go to then you download the medium resolution and then the high resolution, and then you're like, wow, you know, like it's full of stuff, it's full of galaxies, it's full of arcs, you know, that it's just mind blowing.
I did see some people, and I don't know, Jasmine, you'll know because you've you know, got a really good presence on Twitter as well. I saw some complaints on some live streams that I did of people saying, I wish they'd have waited and done the same integration time that they did with Hubble and see even more. Oh, it's another deep field. Some people kind of being a little bit disappointed, but I don't think that gets the point of the fact that they were able to do this in such a shorter time. So there's 2 or 3 kind of variables working together there that they're not necessarily being fair.
I mean, it's great to compare Hubble and Webb, but they are very complementary still now. You know, like we really hope Hubble stays operational a few more years because, you know, especially in the field of exoplanets, you can get really high quality transmission spectra in the visible with Hubble and in parallel in the infrared with Webb. You could even, you know, have some simultaneous data taken, though Hubble orbits the Earth, so it's kind of cut every hour and a half, you know.
Yeah. So Hubble is not dead. Anyone like it's still going to be producing.
It's not yet dead. It's fully old.
Like so people get the idea that it like turns up and like destroys it and just sort of replaces it, but
I actually made a meme about that.
Some images, because of the difference in wavelengths, some images of Hubble in the visible are exactly as sharp as the images of Webb in the infrared. So in a way, Webb is a little bit more of an upgrade of Spitzer than it is of Hubble, but it's a little bit of an upgrade of both if you want.
So you have to be careful with the comparisons. Jasmine, did you say you made a meme about this, Jasmine?
Yeah, I did. I'm gonna post it today. Okay. I've been waiting because I'm kind of scared, like I'm kind of scared that people will misinterpret it. Okay. But I'm sure you guys have heard of that meme where it's like the dog dies and then he sees the Grim Reaper and he's like, was I a good boy? And he's like, no, I'm told you were one of the best. So I did it with Hubble and I photoshopped Hubble in there and he said, was I a good telescope? And he said, no, I'm told you were one of the best. But obviously Hubble's not dead. It's not going to be, it's going to be in operation at least until the end of the decade. But I still wanted to post it because like it's kind of funny. So we'll see. I
think the meme game on astronomy Twitter this week has been very strong. So I think you'll be.
Yes, I'm going to post another one. I have some ideas.
Good.
Yeah. No, but it's just like comparisons are nice, but at some point, I think it's just nice to look at the images and the data for itself, kind of, you know.
Yeah, there's a little bit of maybe being like you said, they're complementary. There's a little bit of competitiveness there to want to be better, but we need the information in all of the different wavelengths to be able to tell everything that we want. So let's get into the images then. So that's some nice preamble. In terms of the images, the first one that we saw, so the images are basically designed, as we said, to hit these kind of major science themes. So looking as far back into the universe as we can. So looking at these super high redshift galaxies, understanding the evolution of the universe, looking at the interactions of galaxies and the evolution of galaxies, looking at exoplanets and their spectra, and also looking at stellar birth and death. So the first one we got was this beautiful deep field. So Julien, what do you make of this deep field? Anything that you want to pull out of this that you think people should really know about? You were talking about zooming in, and if you do, everywhere you go, you just see new galaxies popping out of the image. all over
Yeah, I
the place.
mean, and some galaxies are just beautiful, you know, they have shapes that no one expected. So, you know, like with the Hubble Deep Field, we already knew there were galaxies everywhere, you know, like you could, you know, point the telescope for a very long time at a tiny patch of sky for so long, and then you would realize that it's actually full of galaxies, and each galaxy has hundreds of billions of stars. But in general, when they were highly redshifted, so basically really distant and really close to the beginning of the universe after the Big Bang, they were not resolved. You know, you couldn't see their shape. You could just see like a little blob, and it's by spectroscopy that you would know how far it is, you know, and how early universe it is, if you want. And in this image, you see a lot of highly redshifted galaxies. So galaxies that are super far away and super close to the, you know, to the Big Bang in a way, and they are still resolved. They have shape, and they have like you can interpret that, and you know that, you know, making a spectrum of each of those, it's a wealth of information, you know, and that's not going to be with this image, but that's going to be with NearSpec, for example, or MIRI, that have spectrographs. The other thing I make of this image, I mean, people complain about the diffraction spikes of the few bright stars that you have there, but I find them beautiful. And it may be a bit more than people expected, more than the Hubble diffraction spikes, you know. But seriously, they are bright, those spikes, but you can see really faint stuff right next to them.
Yeah.
And that means the optical quality and contrast is incredible. You know, you can see, you know, really, really faint next to really, really bright. And that, for me, you know, I'm a high contrast person. I love that.
It really is amazing.
And I'm wondering if are there, you know, the other thing I'm wondering, we see all these galaxies, it seems like everything else behind those few stars that are basically really close are galaxies, but there might be a few brown dwarfs, for example, in that field, and we have to find them, you know. And so that's pretty cool. And then the last thing I would say is that you see those galaxies interacting with each other, and you see also the warped, the galaxies that are warped by the gravitational lens around the center. If you unzoom a little bit, those. And this one in particular, you know, somebody, I forgot where in a feed I saw, was like, what is this, banana or something? And, you know, you can see that it's actually the same galaxy that you see twice.
Yeah.
And if you zoom in a little bit on the top and the bottom of that banana thing, that maybe.
Yeah.
No, so yeah, here.
This one.
You can see there's like a faint bit that's a little bit blue.
Yeah.
On the inner end, here, and it's on the other side, it's there too, you know.
Yeah.
And that's crazy, you know. Like, usually we knew that this phenomenon of lensing, you know, gravitational lensing, and we knew it could create arcs, and it could create so it's bending the space-time fabric, basically, and the light doesn't travel in a straight line anymore. It kind of goes around, and it's amplified by the galaxy cluster in the center that's very massive. So those galaxies actually are in the back, and they are magnified like that, right? And so we knew that they could have, like, you could see them double or quadruple. Sometimes we have what we call an Einstein cross, where you see like 4 times the same thing. But I observed Einstein cross when I was working at the Parallel Observatory, but it was like unresolved Einstein cross, you know, like blobs. And here you see like details there. That's crazy. It's
amazing. And Jasmine, you were talking before about this interplay between the beautiful images and the spectra. So a really cool thing in this case is that you can actually, and this isn't the image that shows that, but you can actually take the spectra of these individual galaxies, and rather than having to sort of guess anymore which ones are lensed, you can just take a spectrum and a spectrum of 2 different places, see if they're the same, and you can see which which bits are the lens bits. We can actually get these spectra, these compositions of all of these galaxies, which is really amazing, isn't it?
Yeah, I think so. I love looking at that type of thing compared to, the image.
Yeah, so I guess that the beautiful thing about this is that they've taken the spectra of one of these little red jelly beans in the back, which sort of Julien was mentioning. So these deeply red-shifted galaxies that are in the background, these little red jelly beans, if we zoom in even more, they can take the spectra of these, which means we can get the idea of the composition. And then I guess, Julien, we can get the composition of galaxies as a function of redshift and therefore as a function of time, and get some idea about the evolution of these galaxies and how their contents change with time, right? That's something new that we haven't been able to do out to these redshifts before.
Yeah, it has been done a little bit with Hubble and also with a few spectrographs on the ground, but stacking up hours and hours and hours of data.
Yeah.
And usually the detection threshold was really close to zero, like we say, like in number of sigma, like 2, 3, 4, 5 sigmas, maybe detection of redshift 8 galaxy, for example. And here, this image was taken, so it was 12.5 hours, but it was about 2 hours per filter only. So it's really quick to get to those redshifts, and when you see like the signal is pretty high, and so the spectrum is beautiful, like those lines stick out, for sure. And so this composition is what you expect, but you don't know where it is in the spectrum because it's redshifted depending on where the galaxy, how far the galaxy is, and how long the light had to travel.
Jasmine, the thing that I really like about this this image is like you've got these beautiful spikes. It almost looks to me like the kind of spectrum you would put in a textbook to say, look, this is what a spectrum should look like. The noise is like so low, like here's the 0, and it's wobbling around pretty close and pretty constant. And then you've got these beautiful spikes that definitely show you what you've got in these for the composition. Like there's you don't have to like worry and try and dig through the data. Like it's so clean. Like it surprised me at how clean the data is.
Well,
it's crazy.
Yeah, this slide obviously was made a little bit to explain very in a simple fashion what you have, but it is true. It is true. That's what I was saying. The signal to noise of those signatures are going to be way easier to use, and obviously, if they look for even further objects closer to the beginning of the Big Bang, I think I'm not a specialist in that field, but I think Webb is going to be able to look back 13.6 million up to 13.6 billion years, which is about 200 million years old from the Big Bang. And then you can't see anything. Everything is opaque. It's the reionization, I think.
I've got the,
but it's let's say like the few million years that Webb can look further than Hubble, basically, is what we are talking about, exactly. And so obviously, like in some case, it's also going to struggle, for the faintest ones. The spectrum is not going to be as clean, but that's the whole game.
Yeah, it certainly is. Right, Jasmine, I want to bring you in on the next one. I want to go to WASP 96b, because this is kind of very much in your wheelhouse as a planetary scientist. So why are you so excited about WASP 96b and what exactly is it and what's going on? What have we seen this week?
Yeah, I mean, the reason I'm really excited is just because the field of exoplanet science is so new.
Yeah.
It's, been around since about the 90s. maybe something like that. And so it's just so crazy to think that since this field started, we've already discovered and confirmed over 5,000 exoplanets beyond our solar system. And the fact that, we're living in a time where we're able to get, this transit curve and these spectra from these planets is just so incredible. And I think, people always say, oh my God, James Webb will find aliens. I don't think it will. I think it'll just help us confirm like what worlds are more likely to be habitable over others.
It's quite possible that we'll find an Earth-like planet, I guess, in the next kind of year, looking at these kind of things. So these beautiful spectra that we got. So WASP 96b is a huge exoplanet. It's basically kind of Jupiter-like, orbits close to its star, 3.4 days to go round, which Julien was saying, it's really nice to look at something like that because you can get a lot of transits and be sure that you're seeing something sensible before you post these images. But what they wanted to get was really the spectra of light going through the atmosphere. So you've got a tiny planet passing in front of the star, and you want the light that's passing through the atmosphere and how the atmosphere changes the spectra of the light that goes through. Now that's incredibly difficult, right? Because you have this tiny, tiny planet and you have this tiny thin atmosphere on the side, but Webb has been able to do it, and it's been able to actually give us the when I can find it, the actual composition, the actual spectra of the atmosphere of an exoplanet which is over 1,000 light years away. Julien, that's remarkable.
Yeah, what you see is basically exoplanet weather, or meteorology. I was the other day. So in my team, we have the person that published this planet in Nature using Hubble data, Nikolai Nikolov.
Yes.
And he was telling me that
I think we've got his old. I've got his old plots here. I think they're
exactly. So that's the spectrum. That's the spectrum he got from previous data. I think Hubble and Force 2 at the VLT. And so he told me that his hypothesis was that if you could observe it in the infrared and make a spectrum, you would see mainly cloud-free atmosphere with a lot of variations. Because if it's really completely cloudy, it's pretty flat what you get. And that's what we see apparently.
Amazing.
So there are clouds, like it's not like completely cloud-free, but it's not completely overcast.
It's amazing that we can have some idea of the weather on a planet that's over 1,000 light years away. That's absolutely insane, Jasmine.
Yeah, that's fun fact. That's part of the reason why I double majored in atmospheric science is because, planetary science is such an interdisciplinary field. You can study anything about other planets, right? Like their geology, their chemistry, physics, whatever. And so I kind of wanted to specify what I wanted to study a bit. And I wasn't really interested in geology. Sorry to all the geology friends out there. So I was like, what's the next best thing? Oh, atmospheres. So I've always thought, weather on other planets is so cool because it's so different than ours. It's so, unimaginable how fast the winds are, how intense the storms are, how big the storms are, with Jupiter's great red spot. So that's part of the reason why I double majored in it, because I think the meteorology is just fascinating too.
So not only can Webb discover these things and tell that they're there, it can also go about finding these composition. And I guess that's really useful, Julien, if you want to understand maybe the composition of those planets, how they potentially came to be, because if you look at the variety of exoplanets that we have, it's like ridiculous. And I don't think we have a kind of fully worked up picture exactly as to how these planets come about. What environments do they turn up in? Why do they sometimes have these crazy differentials of size? Planet formation is actually something that we don't necessarily have a full picture of. So understanding what's in the atmosphere and some of the building blocks that are there is really important for getting a bit more of a handle on planetary formation, isn't it?
Yeah, the gallery you're showing, it's actually just the Kepler planets, I think. So
that's a really cool video.
It is a cool video.
But it's not even all of them. It's like those are mostly
I want to make
short,
that into like a GIF or something.
Yeah, those are short period planets, like the ones you can do transit on, because the long period planets, you would have to be very lucky for them to transit when you're looking. And that's the ones I study, in fact. So the whole demographics of exoplanets, it's super important, because you get a bit of a benchmark of everything that exists, and you realize that it's quite different from the solar system, from what we always compare to. Also, the solar system now is 4-point-something billion years old, and most of the planet we can image directly are super young. And those are young and old, I guess, a little bit of everything. And so you have to reconstruct the whole puzzle of planet formation and migration theories out of those demographics.
I guess we're super biased as well, right? Because we can only kind of see ones that are kind of straight on relative to us on the sky as well. So we have a kind of attainment bias as well with the planets.
Observing bias. Yeah, I mean, you can never. I mean, we are biased in the plane of the galaxy usually, and we are biased. I mean, everything that we do with exoplanets is next door, right? We don't look at planets in other galaxies, so we're biased that way. But it's already a lot of things to look at. Practically, you can imagine there is a planet on average around every star you can see in naked eye. It's pretty mind blowing. We know that now. We didn't know that 20 years ago.
And I guess now we have to build up this with Webb. We'll be able to build up some basically a statistical sample, and when I can get out of this image, and sort of understand that planetary formation better. So that is a really useful thing. I would just wanted to show you
I just wanted to say one more thing here.
Please.
So Webb is not the best machine to discover planet transit, because it's very time consuming and it's a big telescope. So you don't want to do what Kepler and TESS and other telescopes are doing, which is kind of like having wide field of view and trying to see everything that's variable and trying to find planets. It's more like it's going to study and characterize the planets that are potentially interesting, already detected by other missions and other telescopes, and find out what they have in their atmospheres. In direct imaging is a bit different. We may actually find a couple of new planets, but there are less anyway.
So we don't want to waste time using a hammer when we should be using a screwdriver, right, for finding planets. It's not the right thing to be doing to use Webb to do this. But it's still some of the comparisons. Therefore, we shouldn't probably quite make, but it still does do a beautiful transit, Julien, if we bother to do it. So it's nice to see anyway, I guess.
Yeah, maybe one more thing I could say, it's slightly more technical on this, to get a curve like that. So this is not a very long phenomenon. And each beam, so each little dot you see here is a photometric point that basically we're using a tiny field of view of Webb, but we're trying to be very precise and very fast at measuring how bright it is. And because we're in space, it's actually pretty easy because things are super stable. So the only thing you have to worry about are like cosmic rays hitting the detector, and detector effect. The detector is sometimes has bursts of has its own personality in a way. And so everything is about cleaning as much as possible and measuring that signal as precise as possible, so that that curve can be as thin as possible and meaningful as possible.
Makes sense. So I want to move on to so we can get through these in good order. So the next one I want to come on to is the Carina Nebula, which, Jasmine, I have to say,
That's my favorite.
it is my favorite as well. Julien, which one's your favorite out of these images? I've seen this like being put on people's doors, on people's screensavers. Somebody's put it on a mug. Like, it's my favorite because there's so much going on in this.
I don't really have a favorite, but this is definitely closer to my field of study, right? I look for planets around young stars, and this is full of young stars being formed. And I also worked a little bit in detecting some jets, and you can see jets here inside. So, I mean, this is a stellar and planetary nursery that you see here.
So, Jasmine, do you want to tell us a little bit about this? Because I think you were talking earlier about the Mystic Mountain. So if we look at this in Hubble in the visible, tell us a little bit about what we're seeing here.
I mean, essentially, it's just stars being born. I think that's the best way to put it. Nebula is a bunch of gas and dust, and it's essentially a stellar nursery. And I think that's beautiful. You know, imagine all the worlds that we're seeing in just that image, and then compare that with the Webb image. And there is actually a Hubble image of the exact area that James Webb image, which my comparison, unfortunately, was Mystic Mountain with that one, but then I found the other one and I compared them. But this will have it, yes. Yeah.
So we can see as we go across. The beautiful thing about this, Julien, and you'll know being a NearCam guy, is when you have it with Hubble, you can see this beautiful form and what have you, but you can't really see inside to what's going on. And when you go into that infrared, you basically it's almost like opening the curtains to see all of these stars inside being born.
Yeah, so you basically go, you can see through some of the dust, and that's why you see more stars. But you still see dust, the dust that is actually at the temperature that correspond to the emission in the infrared, right? So it's very complementary, and then you do it with different filters, and you can reconstruct a sense of what you're looking at, and then you can also point a spectrograph at certain regions.
So what's the idea with the science here, Julien? Is this that we want to understand how stars form out of those clouds of gas and dust, and that the more complementary information, the more wavelengths we can get, we can see, you know, where are these jets of gas and dust? How do the stars interact with the gas and dust? Where do the big stars form? Where do the small stars form? How do they interact with their environments and each other? Is this kind of the idea that if we can see inside, we can get more of an idea of how stars actually come to be born? Because we've got that simple idea of, you know, gas collapses and, you know, we start stellar fusion and it comes into balance, but we don't actually have a full picture of how that what sort of environments lead to formation of stars, right?
So yeah, I mean, full picture is always what we're trying to reconstruct, but so this this big field of view image, I mean, first you're in awe looking at that because it's beautiful and it's full of stuff that people have made theories about, you know, like you must have clouds that basically collapse to form a star, etc. You can see it live in different places in this image.
You can see like the density fluctuations and the sort of ripples in the cloud as well.
Yeah, and but then, you know, like, what do you do with a wide field image full of stuff? Probably, you know, you need to analyze. You need to. It's a little bit of big data at this point now. There's so much information that we're gonna have to look at
machine learning and try and see the patterns.
Well, not necessarily, you know, you can do it the way you want, but the goal is to analyze each of those stars that you see here and try to understand how young are they, you know, what are their chemical composition, what's going on. Can you find circumstellar disks? Can you find, I don't know, brown dwarf forming there, different masses of stars forming? And you can find jets, because often, you know, you have this accretion process, so you have like material rotating around the star, and in a way it's infalling also onto the star, and sometimes it's ejected in some kind of jet or outflow, and we see some of those here. We see some jets directly, in an image that's just for purpose of PR almost, It's crazy. It's crazy the amount of stuff that you can study in just an image that took a few hours.
Yeah, I'm scared that this took like 12
like
hours.
everything that you see, about all those 5 science examples that were released were taken in about 3 days. And
amazing
Webb has taken way more data since then.
I can't wait. I can't wait
Tomorrow,
to see
the archive is gonna explode.
yeah. we've got one on there already. I don't know if you were involved with it. I think there's the science performance. Performance for commissioning is already up on the archive. So
I'm super proud of this document. I made one figure.
Yay!
So
that's enough. That's enough to be involved, Julien.
No, I make figure 12. I think it's figure 12. I'm one of the 600 authors or something. But what I find great, I know very well the people that put this together. I find amazing that the first day we're showing the images to the public, they already took the time, on their weekends and stuff to make this document available. It's like a first. This is what this is a summary of what we know, and
I'm trying to find figure 12 now, Julien. I'm desperate to find figure 12 now. You deserve your moment afterwards. So there's the spectrum we were just talking about. There. This one, no,
it's not. So
it was on the other page.
Maybe it's not 12 anymore.
Oh, maybe it's not 12 anymore. This one?
It's the contrast curve. Yeah, this one.
Right.
That's my
amazing. So tell me what we're seeing here before we move on.
Yeah. So maybe I don't want to take the whole discussion on this because I can talk hours on that, but that's. Basically, I'm in charge of near-cam coronagraphy at the Space Telescope Science Institutes. So together with the colleagues in Arizona, we just commissioned this mode. This observing mode of Webb was not ready a week ago. And so I was the last one. I don't know if you remember the Where is Webb the segments that had to be ticked off. I was the only one, my mode, quote unquote, was the only one that was not ready.
Oh dear.
And that's why, I canceled my vacation, I canceled the conference, I sent the family over to France, and I'm here alone working my ass off.
And that's why Julien deserves his glass of champagne
exactly.
to be ready.
This is July 12th, and on July 10th, I was presenting the mode to the Readiness Review Committee on Sunday, from at 1 p.m. That's when they declared the mode ready for science. And that picture went the day before into the report. So that picture is just a contrast, what we call a contrast curve. It tells you how sensitive you are, from the star to a bit further away, how sensitive you are. And, we're talking about contrast of 10 to the minus 6, 10 to the minus 7. So that means this dashed black line, the one that is the lowest, means that with a little bit of processing and subtracting a star to your science star, you can probably find a planet that is a million or a few million times fainter than the star around it,
Amazing. So Jasmine,
the whole goal here is to do direct imaging of exoplanets. So not the transit technique, the direct a picture of an exoplanet.
Oh wow! So Jasmine, before we move on to the next one, why is this your favorite? And I'll tell you why I think it's my favorite.
I just think it's so beautiful and so detailed. Like when you think of a space image like this, something like that just comes to mind. I don't know. And like Julien said, like you zoom in and you find something new in like every corner of the image. And I think that's just super mind-boggling. I haven't gone through and like zoomed in so much and like done it yet, but I know that is, how sharp the image is you can zoom in like so much and just find, a new star in every corner.
I think there's also a really nice, the fact that it's stellar birth as well. and we think of ourselves as being connected with stardust and all these kind of ideas. So I think when people look at this, and particularly when they look at astronomical images, I think astronomy has a real leg up on say, I do particle physics, because it makes us feel small, but it also makes us feel connected. So compared to being on Earth, everyone is on Earth, but Earth is just like nothing. It's just one pixel out in the universe. Compared to looking out as Webb is doing, we're all in one place. We're all together, and we're all kind of nothing relative to this. I mean, Julien, what's the kind of scale of this thing? Because it looks like, oh, it would just be, you know, it's one cloud of dust. But I guess there's thousands of stars here, so it must be sort of hundreds of light years across this thing, right?
Yeah, I don't know the answer exactly, but the stars are never very close to each other.
Yeah. They're always like 1 or 2 light years at least, like apart, 2 or 3 light years apart, right?
Or I would say many light years apart. I don't know, across, yeah. And so something I thought when I first saw this image was, you know, I know there's nothing political, but I thought, oh, that reminds me of Ukraine right there, you know, slightly. And I was like, oh, wow. I tweeted, you know, like nothing political, but this looks a bit like the tumult that is going on in Ukraine. And then I was like, you know, Webb is really the best that humanity can come up with. You know, it's one big machine. It takes 20, 30 years to make and succeed, but
the Europeans, the Americans, the Canadians, scientists from all over the world as well.
You know, it's not going to give you back a paycheck to everyone, you know, only to us. No, just kidding, but it's really benefiting everybody, you know, like just like making us dream, making us understand our position, or, you know, position in the universe, which is kind of like nothing, in fact, even though we can make this, you know, so it's a very ambivalent feeling. And and knowing that the world is not necessarily in a good shape right now, you know, this is a very complex, positive mix of feelings.
Jasmine, I have to say that the outreach from people like yourself, people at NASA, has been absolutely amazing on this, right? That the whole of Twitter has been like wall to wall with these images, and everyone from all walks of life has been interested in this. I was saying to Stephanie before when I chatted to her, I said, even my mum like gave me a call and was like, have you seen these images? And she's like not involved with science at all. She's actually quite averse because she finds some of it scary and, you know, too hard. But everyone has been engaged with this, haven't they?
Yes, I think that's part of the reason why I do what I do, is because I want the public to get excited about these kinds of things. And I tweeted yesterday, I was like, you know, Carl Sagan would be proud if he could see these images. And I think proud is obviously an understatement, you know, because of how involved he was and how passionate he was about the universe or the cosmos, and, you know, sharing that message with people. And I think that's why I love what I do. I love science communication, especially when it comes to astronomy, because I think people should care about space in some, you know, way or another, because that's our home, you know, that's where we came from.
Yeah.
Really, really important messages.
Yeah, I will admit I felt like a little bit envious that I wasn't working on the project, because I remember in 2012 when we had the Higgs boson at CERN, you know, everyone was like sort of looking at us and stuff as well. But I'm just so happy for the people like you, Julien, who's worked on the project. It's been so long coming that it's finally sort of out there. I'm just so happy to see the results. So we've got 2 more. One is the Southern Ring Nebula. So they're here in the...
I love this one.
You like this one? All right, you can lead on this one. So tell us a little bit, Jasmine, about what we're seeing in this. Where's the? Let me get the new image.
The Webb one is.
Yeah, the Webb one.
Yeah. Oh my God, that one. I don't know. To me, it looks like, I don't know if you guys agree, but it looks like an eye.
It does.
Like the sharpness of that image. Like I've seen those like the videos where like you zoom into an eye and you look at the pupil. Like if your eye was brown, like it would look like that, you know. I don't know. That's crazy. I've seen people do comparisons of it, when they talk about humanity coming from the cosmos, like they do comparisons like that.
Yeah.
But no, I really like this one because, like I said, the sharpness of it, and also just how much like we can see in comparison to the Hubble one. Like I don't know if you have the website pulled up where it's like
I've got the
side by side.
Yeah.
Yeah, it's just, to me, this one was like, besides the Carina Nebula, this one was like the biggest like night and day difference between Hubble and Webb. Because like, look at that, it's like, oh my God, we're peeling back the curtain and able to see so much more than we were before.
And not even just in the middle, right? All the stuff in the background
even in the
that
center.
sort of comes out, like
So I read somewhere. So also there's the MIRI image of this one, which is amazing because in the MIRI image at longer wavelengths, you see that the central object is the double star, and that was predicted in the past. And in fact, I think the person that published that only got 5 citations.
I saw that.
It's about to change,
Maybe I can. I can't remember if. Where is that? Do I have that? I think I might have retweeted that today. Let's see. So the guy suggested this. I think it was like quite a long time ago as well. Like my thing is just rammed with JWST stuff.
Not the most famous. The Ring Nebula, not the southern.
Here we
Ring
go.
Nebula.
I've got it. There we go.
Okay, 68.
Yeah. So he suggested that this might be a binary star because of the ionization balance which is going on, and like you said, he only got 5 citations for this. Nobody was biting really, but then when we look at it in the mid infrared, like you said, we can make out these 2 stars. So I think
this image in particular, the MIRI one. It may not be as good looking as the other one, but it really shows the power of MIRI.
Yeah.
That red star on the left it's just too faint to be seen at other wavelengths, and in the mid-infrared, it pops out.
Is that because it's cooler, Julien? Because it's cooling down?
Yeah, so it's colder and it's redder, and so you can, and also there's probably stuff in front of it, that makes it more obscure.
So we've got this beautiful, and again, we're sort of hitting one of these science goals, right? So this is the Southern Ring Nebula, or 8 burst nebula. So the idea is these stars in the middle have died, puffed off all of their outer material, and you've got this essentially bubble in space, which is sort of cooling down as it sort of expands out from that one dying star in the binary. So it's a mix of sort of life and death, if you will, Jasmine, as well. So we got the birth in the nebula, and then we've got the death here with the
I remember making a tweet about that a long time ago, comparing stellar birth with stellar death, and I used like 2 images, but I think that I might have to do that again, comparing stellar birth with stellar death, because honestly, it can be said, something poetic about death and whatnot. But yeah, this one is about 2,000 light years away from Earth. And it's gorgeous. I don't know what else to say, really. I love it so much. I think
so this is like
so much in there.
I think this is like the gentle death of a star. Is that right, Julien? Rather than the supernova of a huge star, this is sort of the red giant phase that maybe our own sun will go through in several billion years. So it's maybe a nice sort of view into our future as well.
I don't know the specifics about that one, but I would assume you're right. So with our own sun, it's not big enough to turn into like a black hole or anything, so it's just going to expand over the next several billion years, and then eventually, as it expands, the climates of the planets are rapidly going to change, and then also the first few planets up until Mars, I believe, are going to be swallowed. But I think we'll be long gone by then.
We're gonna have a good suntan on that day. Exactly.
Yeah.
The amazing thing about this one, Julien, as well, you were talking about the different cameras, is also that you can you can still pick up, even when you're not even trying, these galaxies in the background, this one being an edge-on one. Like, without even trying, you're looking at something specific, looking for the science of this planetary nebula, and all the time you're picking up all of these extra galaxies that we've never seen before in the background. It's almost kind of money for nothing.
Yeah, I mean, seriously, like, I don't study galaxies. I'm like, how are they gonna, study all this? It's just too many everywhere, and the morphology and the taxonomy or whatnot, except so. Yeah, in fact, what I'm thinking is that it almost becomes difficult to study stars because you're like photobombed by galaxies.
Yeah, how do you make a decision on like what to look at? Like it's
at the precision of JWST, there will almost always be a galaxy overlapping your field, or your object. So, but it's just mind blowing.
At least I guess we're going to be able to get a really nice sort of angular distribution, right? Distribution on the sky of all these different galaxies as well. So not only can we do that sort of time-based, distance-based evolution, but also in terms of directions in the sky as well, we'll be able to get such a huge data set that we can start to sort of nail down in all directions and back in time at the same time. So, I mean, that's going to be absolutely amazing. I mean, it's just a beautiful image as well. There's no doubt about that. So the final one, because I don't want to take up too much of your time, is Stephan's Quintet. So Stephan's Quintet, and we've got it beautifully in a couple of bands. We've got it in Miri and in NearCam as well. So let me zoom out a little bit. So this
one's really cool.
This one is really cool. So Julien gave me a kind of nice segue in there because this is a compact set of galaxies about 290 million light years away. It's called Stephan's Quintet in Pegasus, and it's notable for being the first compact galaxy group ever discovered in 1877. So there's kind of a nice historical callback as well from this being the first and now finding much more out about it. And 4 of these galaxies are sort of dancing around one another, and the large blue one here is actually much closer to us, but it's kind of superimposed on the sky. So I guess the idea is here that we're going to get some idea of how galaxies interact, how galaxies evolve, and how those earlier galaxies that we saw in the deep field images, how they evolve, come together, interact, and we end up with the galaxies that we see more locally with spiral arms and such like the Milky Way. Is that sort of the idea here, Julien?
Yeah, that's the idea. I mean, there's so much information here again. And this is the mid-infrared image, so it looks a little bit like clumpy, if you want, because you see like the big, you see certain type of cold dust here. And not so much the scattered light that you see in the visible.
We got some. We got the NearCam as well.
Yeah, so this is this is NearCam. So this one, when I saw it, on a slide, not so high resolution, I was slightly disappointed because the Hubble image is amazing, But if you zoom in,
we got the Hubble there as well.
Yeah, that's the Hubble image. It's magnificent. Yeah. But if you zoom in on the high res one, that's crazy the amount of stuff that you can see here. Is that the high res?
I think it is, but I'm not too sure. You can start to resolve like single point stars.
A little bit more, even more on those arms, You can see stars, and you can see basically, you can guess the number of stars that are there here. Like it's really not just washed out by the angular resolution of the telescope, And then on top of that, in the back, you see it's a deep field,
We've always got the deep field for free.
And so I really like that image. I mean, I find it really, really, really mind blowing.
The amazing thing here as well in these images, and I don't know if you posted about this, Jasmine. I don't know if it was you that saw this. That we've got an active galactic nucleus as well. We've got this huge black hole as well, which is swallowing up gas and dust. So we see this gas all piling into this black hole. So we've also saw a black hole in these images, which is like ridiculous what Webb can do.
I think it's not this one though. I think it's the one with the diffraction.
It was a different one. Yeah.
It's the one with the diffraction spikes.
Ah.
Yeah.
Okay.
I believe that's the one that's the black hole.
So which one are we looking at?
Oh. Okay, wait.
we want to be accurate. I can. Is it not this one?
That's in Miri. Yeah, exactly. That's this one. That's in the Miri image. So maybe it was the one you were showing, but in the Miri, I remember that one.
I want to make sure I'm accurate, but you can't see this in the Hubble image. Well, you kind of can, but not as.
Yeah, you could guess that it's an active galaxy, but you don't know, right? Until, I mean, here it's like there's like a tiny source. I mean, in terms of, it's not tiny, but in terms of angular size on the sky. It's not resolved. It looks like a star, you see the spikes of diffraction, but in fact it's a super active place. So it's basically swallowing a lot of stuff, a lot of stars and spitting them out.
And Jasmine, coming back to your kind of thing that you said at the start, with the data just being as important as the images. Tell us a little bit about this one.
Oh gosh, I'm gonna try to zoom in. I mean, you can see the same thing with all the spikes there. I think that's really, really important. And, we're finding that this is around an active black hole. So I think that's really, really cool. And I think I was talking with someone yesterday in the space that I did, that most galaxies are discovered to have supermassive black holes at the center of them, including ours. So obviously it's nothing to worry about, but it's still so cool to think about that and the fact that we're seeing one right now.
I mean, we're gonna have to understand them better, aren't we? Because they do seem to be at the center of all of these galaxies. So maybe people have this idea of black holes as like, incredibly dangerous, like incredibly destructive. Yeah, but maybe we owe the fact that we're even here to the fact that we have these, these cosmic behemoths and how they actually interact when these galaxies merge.
Yeah, that's definitely something to think about. And I think that's part of the reason why I think this image is really, really exciting too, is because 4 of the 5 galaxies, they're so close together, they're interacting with each other, and at some point they're going to merge.
And hopefully,
the merging process takes time. It's like a really
it's like a dance, and we're going to be.
It's going to take.
The Milky Way is going to be doing that with Andromeda. So we're going to be colliding with Andromeda, millions of years into the future too. So.
Don't people panic? It's going to be a long time in the future.
Don't collide much. The stars actually. So it's a bit like being a mosquito and flying through a big net. You don't touch it.
Yeah,
but you have those gravitational interactions still, though. No, it's really fascinating. And if we have these compositions, we can get an age, we can get an idea, we can, know how these interactions are going to happen. And I guess if we can look at, hundreds, thousands of these potential mergers around the universe with Webb, we can start to build up again a statistical sample and see the different stages of these mergers, and hopefully then be able to build up a computational model about how these mergers actually happen, Julien.
Yeah, and that's one of the questions. So again, not extragalactic astrophysicist, but
neither am I. So I hope I sort of said something sensible there.
I know that like do AGNs, for example, do active galactic nuclei or black holes have a role in triggering the star formation? That's the question, and when, and for which type of galaxy, etc. We know, for example, we know in star and planet formation that they are contemporaneous, right? The planets start forming when the star is not finished forming. It's kind of it goes together. It's almost like a fractal, if you want. And but then the question is, where is star formation happening more? In which type of galaxies, for what reason, etc. So yeah, the spectra are very clean also, and you can do, I guess, Lang strength ratio. You can measure you have also information on the dark matter that is usually around galaxies.
They got velocity data as well on the how quick the stuff is going around the black hole from the redshift differential.
Yeah, so you get velocity fields because basically each of your pixel is a spectrum. If you have an integral field spectrograph, which is the case for MIRI and NearSpec, NearSpec no, but MIRI, and so yeah, you can see what's coming towards you and what's going the other direction, and so you have a sense of the speed. You get galaxy dynamics basically, and with that galaxy dynamics compared to models, and you can determine what's the mass of the black hole, for example, what's the dark matter mass estimation around that galaxy, etc.
I don't know if Jasmine, I don't know if you had a feel for this, because I certainly didn't before I did all of this interaction with you great science and astronomer people this week. But I never realized, and I'll say this to both of you, I never realized just how all-purpose JWST was. Usually things are more focused than this. The amazing variety of the things that it can do. We talked even about transits, and Julian's like, we don't really want to be doing that, but it can do it. But it can.
I'm not saying we shouldn't.
He's not saying we shouldn't.
I'm just saying like keep a little bit of time to do coronagraphy.
Yeah.
But just the variety, I didn't realize that. I don't know if you knew, Jasmine, from looking at this probably a lot deeper than I have, just how many things it can do. It's just
I definitely underestimated it. I wasn't thinking about it because I thought, okay, it's going to be really focused on exoplanets and that type of thing, but then we get images like this, and that's not what I was expecting. I mean, I was expecting great images, but that's not the, depth, the amount of depth that I was expecting.
No,
15, really exciting.
Maybe 15 years ago, it was not even thought to do any exoplanets. So it wasn't designed at all for exoplanets. This science case came along the way and became super important. Exoplanets were just a few, the first exoplanets detected by JWST in 95, the Mayer and Kello's 51 Peg B. This is the start. I mean, there were a few those planets detected around pulsars, but this is the start of a long list of exoplanets that were detected in 25 years. And so like some years ago, at some point, people started to say like, oh, Webb is going to be fantastic for that. And that became more and more important. And the transiting, so the time series that we take to get transits, those modes were developed along the way.
Wow.
That's really awesome.
That's like a positive of the delays in the schedule. At least we managed.
At least we got
one of these things in.
Yeah, I mean the preparation for science has changed quite a lot. And then the other topics were actually planned, I think, longer in advance. Understand galaxies and how they form, understand the early universe, and understand the star formation. That I think that was planned earlier on. But yeah, I mean, this is what you call a flagship mission, like Hubble's super versatile, Webb super versatile. And then you have some really, really dedicated missions like Kepler tests for exoplanets, like Gaia for astrometry. Yeah. But in fact, Gaia, every possible astronomer is using Gaia results and data to refine their science results, in fact.
So even I, not an astronomer, excuse me, I'm doing a Gaia project. So I downloaded a load of the data the other day, and I will tell you on email what it is, so somebody doesn't do it before me. It's a very nerdy, like interesting, like human interest idea, and you can tell me if it's a rubbish idea. I'll send it to you afterwards on email. But I've already started, like I've written the code for it and stuff. So I will explain.
So in general, they are like, so space missions are extremely expensive. Money and resources. People. Man and woman power,
Yeah.
and every gender power if you want. so it's those are huge endeavors. So if you put all your eggs in a basket, which is kind of like what happened in this case, and some people were grumpy about it for many years, the mission was almost canceled at some point.
Yeah.
If you put all your eggs in this basket, you better want to have a good basket that does everything. It
needs to be a Swiss Army knife, I guess.
Yeah. Well, you still have to compete. People still have to compete to win observing time. Yeah. But the committee is going to make sure there is a little bit of a spread in terms of what kind of science is being done. So there will be a bit of those four main categories.
I like that they said it was all. Michelle Thaler was telling me yesterday that it's all kind of blinded and done once every year. So it's perfectly just based on the science. It's not some amazing scientist with loads of publications comes along and says I want to do this. It's purely what are the suggestions, what is the science case, and then a group of experts look at all of these suggestions and each year decide who's going to get the time. So it really is dedicated to the best science cases, which will obviously change as we find new things, which is a really nice way of doing it, isn't it, Jasmine? It keeps everyone sort of in the loop, and as we find more stuff, we're going to look at the most interesting stuff rather than just being this was the theory, so we're going to try this. We're actually going to be really on the pulse with this.
Yes, I'm really, really excited. Again, I was too young to experience that with Hubble, so now I'm excited that me and like the younger generation get to have a telescope, get to have life-changing stuff. I think this is definitely the best time for astronomy.
I agree. I think you're gonna have you're gonna have like we had in particle physics when we were spoiled, like between the 50s and 70s, it was like Nobel Prize, Nobel Prize, Nobel Prize, Nobel Prize, Nobel Prize.
That's true.
and since like 2015, it's been astronomy's time is now. It's like the golden age of astronomy. It's become, not only has it become incredibly cool, now the technology is at a state where we can do this level of quantitative detail as well.
Mm-hmm.
So I really think it's going to be the golden
age. There will be I don't know if there will be an instrument as big in our lives or careers anymore. It takes so long to plan a mission, and the next one. So my colleagues and I, because we like to look at even finer details and even deeper contrast, we already are wishing that a bigger mission is on the way.
Yeah. I don't think we'll ever be satisfied.
No one's ever satisfied. We always want a bigger ring in our particle physics.
It's
the next
complementary, while some astronomers are going to have fun with this and publish tons of papers, other astronomers are going to be working in labs, trying to improve optical components and for the next mission to actually image directly exoplanets, Earth-like planets. And that's going to take time, I don't, if I see this in my life, I may probably be retired or an old fart, saying I said this a long time ago,
I worked on this 50 years ago. Yeah.
Which, by the way, sometimes, people are, there are some really great emeritus astronomers, they really started a time where they were doing a little bit of every science case you see. Here, when we are much more focused on tiny ramification of science.
Yeah, that's why I'm really excited for my generation. I don't know what we're gonna discover. I'm really hoping we get some kind of confirmation that there's life out there, because that's what I want to know, but we'll see.
I was lucky to come along when the LHC was just starting. Jasmine, you're starting, I think, at a beautiful time in the field. So,
yes. I really also hope we get an ice giant mission, but that's for another live stream.
We're going to discuss that. We'll discuss that another time, because we might be seeing some images from, I think, from Enceladus and places like this.
I'm
soon. So
I'm excited for that.
Yeah,
right.
Nothing can beat space probes in terms of for the solar system, but Webb would do a little bit of solar systems.
So I want to finish off because I don't want to take any more of your time. Julien, I know you're like probably worn out. So let's finish up. I've just got two sort of personal questions to finish. Come to you first, Jasmine. If you were in charge of JWST and you could point it anywhere you liked,
Oh gosh.
where are you pointing it first?
This might be a weird answer, but I've been really interested in like the I might pronounce it wrong, the Boötes void, just because like we expect there to be so much out there, but there's like such a severe lack of galaxies and stuff out there, and I really want to know more about that void. I'm sure you've heard of it, right?
Anything that's odd we want to know about, right? This is
yeah. Have you heard of it?
I'm not really aware of it actually.
Oh yeah, it's really.
What's it called? Can we look it up?
BOOTES void. Well, the second O has two dots above it, but that's okay. I'm sure
that's okay.
TES and then void.
Oh right, It's come up straight away. So
I'm sure Webb will find
so
stuff.
Interesting.
Nice.
That looks a bit of a weird one, but here we go. Right. So
okay. But that's Barnard's cloud, right? This is close to the
galaxy. Yeah, I think it has something to. Yeah, but it's just
this is dust, and Webb is gonna see right through it, I think.
Probably will. But I don't know. It's just so interesting to me. Like I want to know more about it because it's like why is it's so massive, but there's really like very few galaxies in there. It's
almost like the inverse. It's almost like the inverse, right? Because usually we see everything is rammed full of galaxies and stars, and then we have this patch. So it's just kind of odd to see.
Yeah, and it's 700 million light years away, and I think it's also like spherically shaped, if I'm not mistaken. But it's really, really weird. I don't know if Webb would be able to find out a lot about it, but it's yeah.
Julien, thoughts?
Yeah, so I don't know if you've seen this in naked eye from the southern hemisphere. If you're in a very dark site, you look at the galactic plane close to the galactic center, and you see by eye those dark regions, which are basically really dusty. And so I expect Webb to just see right through it and find a lot of stuff, in fact.
Yeah, it's always interesting to, think about what wavelength you're seeing in. Is it transparent just in the visible? Is it transparent in something else? I don't know. Very interesting though. I want to go and learn more now. So this is why I understand why your Twitter is so successful now, because I'm like right now I want to go find out about this thing.
Yeah.
So you've done a good job on me. Julien, where would you point?
So in fact I applied, for Webb and I was successful and not successful at the same time. Like some proposals got in from that were mostly led by other people. The one I mostly worked on didn't get through, and so that's the kind of things I would like to do, but I'm not alone to do that. It's an army out there. No, but basically, if you look at young stars, so young stellar objects that have disks around them, we see those gaps inside the disk. So the disks are carved in a way by something. And this is something we see in scattered light in the near infrared, but also ALMA, the millimeter.
Is it South America somewhere?
Yeah, it's in Chile, but it's an international partnership. And the ALMA has detected a bunch of, all these circumstellar disks that have gaps in them. And so the big question is like, do planets create those gaps, or are they created by some kind of resonance in the dust and gas and density waves? And can we see those planets? So in a few cases, we've been able to directly image some of those planet being forms, and that's the case of PDS 70 B and C. I was in those discovery for those two young planets. But unfortunately, we haven't been able to be very successful in finding planets in other such objects. So yeah, the one, the black one, it's the PR image, but yeah, you can show one of those sphere images. So like one red and orange image. Yeah, this one, for example, an ALMA image. So in this case, you can see the circumstellar material, which is dust and gas, the bright ring, if you want. And inside there is this huge gap, and this gap in this case was carved by this planet that you see, you know, and this planet is being accreted as we speak. You know, it's it's being formed. So it's a young,
so it's almost sort of like a vacuum cleaner going around, like cleaning up this sort of area.
So this is the archetype of the things we want to see. Sadly, Webb is only 6 meters across, so we're a bit like borderline, not sharp enough to see this. This one we might be able to see, but like really with a bit of effort. But we are trying to find this basically around other stars and understand how those planets form. Because if they form far away, they are probably formed by gravitational instability. So it means it's not formed like the Earth. It's formed like in situ in the disk. And that's a whole one of the scenarios that we're contemplating for planet formation. So it's important to find more.
Really interesting. I'm really happy that you're both interested in basically empty space. Like, nice
exactly the void.
Yeah, exactly.
Because it's so strange to think about, like, because we expect to see so much out there, and then there's just some parts of space that are empty. So it's like, why?
Yeah, that's awesome. I really like that bringing together of your two ideas. Final question. So we can finish up. I'm interested in whether, and Julien, you've worked on this project for a long time, and Jasmine, you've been talking about it all week.
Are we interested in
before that, I'm interested in whether JWST is going to become, like Hubble, a kind of part of the popular culture. So with Hubble,
I think so.
It's sort of like it's the telescope that people know about who don't know about telescopes in space. It's the thing that gets blown up when the aliens turn up in films because people know about it and these kind of things. Do you think, Jasmine, that JWST is going to become a similarly well-known part of popular culture where you say, do you know a telescope? Yeah, I mean, James Webb.
I definitely agree. This is great that you brought this up because I was literally talking about this yesterday in my Twitter space. First of all, we've already seen, like, it's been trending on Twitter for several days now. And I mean, so many people have been tweeting about it, not just, astronomers and all of us in the, tight-knit space community. People way outside of it have been excited about it. I mean, you're talking about your mom. So that's crazy. And then the second thing is, like, what I was talking about yesterday, I was thinking, like, Hubble, we have these really infamous images. Literally, ask someone to think of a Hubble image, they're probably going to have the pillars of creation pop into their head. That's like one of the most, if not the most infamous Hubble image of all time. I literally have a picture of it on my wall that I'm looking at. And I was thinking, I was like, what is going to be James Webb's
pillars of creation?
What is going to be the pillars of creation of James Webb? What's going to be that image where, like, if you tell someone James Webb, just think of it, they're going to think of this image. And that's what I'm really, really excited for. What's going to be that really infamous image? It could be, one of the ones we saw yesterday, or it could be
something
one of the future ones that gets released. But I definitely think this is going down as one of the most infamous telescopes. I mean, we have, like I said, we have so many people outside of the community already talking about it, and that journey is just getting started. So,
and I really like that, Julien, that the work that you guys have done, that so many people have done, is now getting recognition outside of the field. And like you said, it's a beautiful thing to bring us all together, because we're hearing about COVID or wars and things like this. This really is something that can bring us together in thinking about space, our place in it, and how small we are compared to all of this this
Yeah,
surrounding.
I feel so lucky to have worked in such a project. It was a hard decision to come here in Baltimore, move the family, and change field. Also, I was a ground-based astronomer. I had to adapt to this culture of space astronomy. But now I'm a proud space astronomer as well as ground-based astronomer. But I do so. Yeah, to come back to your question. I do think Webb, or maybe it's going to be renamed, who knows, is going to be part of the culture. In fact, I don't know if you saw, but yesterday night at the concert of Coldplay in Berlin, they were showing pictures of
Oh,
the Webb
really?
telescope.
Yeah, NASA tweeted about
on Times Square as well. Everywhere people are
Yeah.
talking about it. So it's very close to, I think, what Hubble was. At least when its vision got fixed.
Yeah.
And because and Hubble, maybe Hubble had something different, was that you could send astronauts to fix it. So like the different service missions with the space shuttle in particular, I guess, for people my generation and a bit older, that was really like something incredible. And Webb cannot be fixed, cannot be serviced like that, maybe by robotic arms. On the other hand, so I used to think it was not going to be like Hubble. It was just going to be for 5 or 10 years. Like its lifetime wasn't also as long as Hubble. But now that we know, the launch was so precise, and we know that it may last for 20 or maybe more years, it has enough fuel for that. I mean, obviously, it's going to be really part of the culture, popular culture.
And when the politicians so President Biden sort of grabbed it on Monday as well, it must be popular sort of across the piece when the politicians sort of want to get involved and get a sneak peek of it as well. So I guess it really has sort of had that impact, which is really, really awesome and really, really good to see. I just wanted to pick up on one point that you said there, Julien. The amazing thing about this telescope is that you were saying people are always thinking about the bigger and better telescope, but you've also now demonstrated that you can fold something up, which is really big, launch it, and then open it up again. So that opens up a whole new field and a whole new technology and way of doing things in space, that we can actually fold these things up neatly, launch them, and then open them up in space to something extremely large. So not only is it amazing in itself, but it's opened up a new way of doing things going forward as well.
Yeah, in principle, we're not as limited as before by the rocket size, basically. And I'm all for like even bigger telescopes in the future in space, but the Webb telescope is going to be a very good argument to show that you can send something super complex and make it work. But the Roman space mission is going to be like, can you do it on time?
Yeah. So very, very final thing, Jasmine.
You can show both, then you can get funded maybe for a bigger one.
Well, quite exactly.
Yeah.
Jasmine, have you seen any ideas about what else might be coming this week? Well, you've been sort of going on Twitter. Can you give us a little bit of an idea? And then Julien, maybe you've got some insights as well. So Jasmine, what have you seen?
I think we're getting some Jupiter images. I've seen that circulating around, and I mean, you have the ones, the test ones pulled up there, which are really, really awesome, even if they're just, not official images that we're going to get. Now, the other ones I was hearing about are not going to be this week or anytime soon, but I did hear that James Webb's going to be looking in depth at the TRAPPIST system, which, that's really, really exciting, because that system has about 7 or so planets in it, and they're all very close to the star, and just that system is really exciting for people that are into the exoplanetary field, including myself. And then, like you mentioned earlier, we're going to be getting stuff about the icy moons in the solar system. I think that's some point in the future. So these are all like future things, but I think the Jupiter stuff is coming out tomorrow or sometime soon.
Because you guys can do it so fast, Julien. Like I can't even keep up with like all the stuff that's coming out. Can you, Julien? Just as we finish, can you give us any insider knowledge about what we might see in the near future?
So, like, first of all, those Jupiter images that we see, I saw them a few weeks ago during our daily briefing. You know, those are engineering images. You know, like one of my colleagues in my team actually just said, "Hey, we should point at Jupiter now that we have the tracking working for the solar system objects. You know, they basically move faster, so you have to track faster." And I was blown away when I saw this the first time, because I didn't, you know, I remembered sort of that Jupiter had rings too. You know, they have been imaged in the past, but in this you could see at the same time a super bright Jupiter, bright star, and you can see the faint rings and a couple of the moons, you know, in the same image, you know, and that also shows that the contrast is incredible. So I was blown away by this, and this was very very interesting, and we massively saturated the detector with that. And so, okay, so something I can say also, like, so right now have started what we call early release science observations. So not the early release observations, which is what you started to see a couple of days ago, yesterday, but the early release, sorry, I get confused. Early release science observations, ERS, and those are teams that have been put together, and they got time to be the first to actually analyze scientifically web data. I'm part of one of those teams that we're gonna do direct imaging. That's what we do. But those teams are gonna get their data starting tomorrow. Not everything has been taken, but what has been taken is gonna go down tomorrow for them. And open the the archive to them, and they are all getting ready with simulations. They have their pipeline and software tools, and I can tell you that in July there will be papers up from these teams, and they are supposed to, in return, they're supposed to share all the codes and software that they're using to the community, so that it's kind of a give thing.
Yeah, we're gonna have to have a dig through that when that all comes out. That sounds absolutely fascinating. I'm going to let you guys get off because I've taken up a lot of your time. I've really enjoyed chatting with both of you. It's been absolutely fascinating. Jasmine, is there anywhere where you'd like to send people to know more about what you're saying, the amazing space stuff you're putting out? I'm going to have all of your links down in the description as well, so people should head over to your Twitter and check that out. Anywhere else you'd like to send them?
Yeah, so I have my Twitter, astro_jazz, and then I also have my blog, which is linked in my Twitter bio, astrojazz.space. I'm sure you can link that, you know, in the description from my Twitter. But yeah, I post occasionally blog posts about just random space topics that I'm excited about. So you'll probably see some blog posts about James Webb at some point.
Amazing. Awesome. I'm looking forward to those. Julien, anywhere you'd like to send people to know more?
Yeah, I'm also on Twitter, so it's my handle is Julik, DJULIK. So it's not very easy.
I thought you were a DJ in your past life.
No, I mean that's what some b-boys were calling me at some time, like in my youth. Awesome. And so it pick up, and also it means kind of thief, a gentle thief in Russian, Julik, you know. So, you know, it was kind of I like that.
I like it too. I'll make sure all of your links are down in the description as well. Yeah. Amazing. Thank you so much, both of you, for taking the time. I know you've been working hard on this all week and you must be tired. So I'm gonna let you go, but hopefully the next time one of these big releases comes out and something really cool is out. I'm a little bit scared to say that because it might be tomorrow now. We can have another chat. It's been an absolute pleasure. And Julien, great to chat to you again. And Jasmine, wonderful to meet you, and both of you keep up the excellent work and the excellent outreach to people with this awesome science.
Thank you.
Yeah, I feel like I'm a regular because I came twice, so that's already several.
You are. You're one of my go-to guys now, Julien. You got to be careful because you get roped in when interesting things come up now.
People are gonna get tired of my accent though.
No. Adds gravitas. It's good. It's good. Right, I'm gonna end the stream. Have a wonderful evening, both of you, and let's stay in contact and let's chat again soon.
Thank you.
Thank you, Sam. Bye, Jasmine.
Bye.